Well, hello. This is M&M team, and we're gonna start to explain a little bit what we're gonna do with part 2 for the lab. Actually, part 3. Sorry. The part that is summertime 2-channel audio mixer. So basically, for this part, we are gonna be building an audio mixer, which is basically sort of a device in which you can connect more than one input. In our case, we're going to have 2 inputs, and it's going to be an iPod, a phone, or whatever, a computer. And then you can mix those 2 inputs. Let's say you have a song that you really like, but then you want to mix it with another song. So you're going to have 2 songs playing at the same time, and you can control which one is louder, which one is less loud, and it's a really cool thing to have if we want to make mixes of songs. So that is the purpose of our little lab part right here. A little bit of how we're going to do it. So first of all, we're going to be using an inverting amplifier. And what this is going to do, it's going to take all the little sine and cosine waves that are going to be emitted by our phones or iPod, and it's going to amplify them so they can be heard through the speakers. And also what we're going to do to control, the amount that we want to amplify that signal is that we're going to have potentiometers which change the resistance, and these potentiometers are going to go right here. Obviously for our little case, we're going to see later on our circuit diagram, but we're going to have more than one of these be in. We're going to have 2, so we're going to have 2 RI, and those RIs are going to be potentiometers which change how loud you can hear it, or how low you want to hear that specific input. A little bit about inverting amplifiers. They invert the signal, but as Mauricio and I were saying, it doesn't really matter for the human eye if it's, a wave that goes this way compared to a wave that goes this way. So it doesn't really matter if it's inverted. What does matter is that it's going to be amplified, and we should keep in mind that this is going to be our result. So we need to find correct values for RF and RI in our circuit diagram later on. Thank you.
So in order to design the mixer, we decided to use, like Maria explained, an inverting operational amplifier. But in this case, we have 2 branches, and this is the circuit diagram. I'll go into detail of what each part does. And these are the component values used. We connected the operational amplifier to plus minus 15 volts. These are like the measured values of that. And I'm going to explain the choice of the other elements. RI1 and RI2 are basically the series combinations of R1 and RP1, which is the pot, and same thing with R2 and RP2. And in order to calculate this, what we did is we found a range for this, our RI1 and RI2, finding pots, 50 kilo ohm pots that work. And we decided we wanted a wave for each branch that's from 0.1 to 10. So basically what that does is we know that the weight is RF over RI, and since we knew the maximum, when we wanted the maximum resistance to get to 0.1, we did this with case 1 first. We found a resistance for RF that was 4.389. We actually found a resistor and chose a resistor that was 4.35 kilo ohms, and based on that value, we calculated the minimum RI, which is 435, and in order to prevent this whole resistance to be equal to 0, and because the amplifier and the voltage start fighting, because then this V minus won't be V plus, that's 0 volts, and that V minus would be the input. In order to avoid that fight, we included resistors that cannot change. That's a minimum resistance, and that's how we chose R1 and R2 that are 423.6 and 420.9 ohms. The benefits of this design are that each branch works independently. We can change RP1 or RP2, and that way change how loud each of those voltage sources will sound. And we don't really care the fact that it's inverting, because our ears hear it the same way. It doesn't matter if we invert the sound. So that's basically what our circuit did. In order to assess whether it worked or not, we grounded one of the sources, and then we found 5 points of different RIs. And those different RIs, we calculated the gain, and by comparing the out and the in with a function generator, and we compare theoretical with measured values.
Hello, so this is our actual circuit for the 2-channel audio mixer. And well, basically it looks a little messy, but these are our 2 pots, which we call R1P and R2P. Here we have our 2 baseline resistors, which, as Mauricio said, we're going to use them just to have a minimum resistance for each V1, which is his iPod, and V2, which is my tiny iPod. In this case, we're using the oscilloscope so that we can see V2 in this case, and then Vn, which is here. The rest is just that we connected the output to speaker so that we can hear it. And we're gonna start turning the knobs so that we can mix our songs, and that's pretty much it. Of course, here we have our awesome op amp and our RF sitting over there. So let's see how it sounds. So this is Eminem about to try our super awesome circuit that mixes songs. And of course on this side we have classical music from Mauricio. And then here we have, I don't know, whatever comes from weird Latino music from my iPod. So let's see. Let's click play. Wait. So this is the V2 and Vn.
And we can test how the difference in sound. Right now I'm lowering the volume of the piano. You cannot hear the classical music anymore. And if I put it up high again, there it is. And it's the same thing with the other one. So total volume.
And now we can shut it off completely.
And we can have our signature mix.
And now we can have them mixed. Awesome piano song. Yay! Hello again. So these are the first results in which we grounded, sad face, the output coming from V2, the input coming from V2, and then we're only using V1 just because we wanted to, you know, keep separate inputs so we could see them in the oscilloscope and not have a superposition of waves. So we tried a different range for our I1, and as you know from the previous videos, our I1 is the addition of R1P and then R1. So these are those values. And then our RF is going to be the same since we're not changing that one for all of them. And this is the expected weights. So that's going to be our F over our I. So these are the expected values. And then to actually measure what we get for the weights, we measure the V out peak to peak and the V in peak to peak in the oscilloscope. And these are the actual values measured. And then we calculate a percent differences. And for the first one, we have a 0%. And as you can see, all of these are within a correct range that we, you know, sane range for our awesome device. So now in the next video, we're going to try to see what values we get for V2 when we ground V1.
Hello again. So we did what we did for V1, but we did it now for V2. We basically grounded the other channel like the last time, and we used a frequency of around 1 kilohertz or 1,000 hertz. We connected V2 to a function generator and measured different values of Ri2, and that's the whole range. So this is the minimum value for Ri2, and that's the maximum value. But we turned the pots completely, and we used those values to calculate our expected weight, and we measured V out and V in peak to peak in the oscilloscope, which we're going to show you, and calculated our actual weight and calculated the percent difference. We must notice that the percent difference is pretty low for all of them. We have all below 5%. And also check this out, when using the whole range, we're getting from 0.01 around to around 10 gain. So that's what we designed for, and we got the same favorable results for V1.
Alright, so now we're going to check out how we did that last point over there, so that we go, to explain how we got those results. So basically in here, this is our R2P, and if we can follow it, we're going to see, this is our R1P, and if we can follow it, we're going to see it's connected to ground in here. So this is the one that we're going to be measuring. Alright, so we're going to see how we got the results that we just saw on the board. So basically, this is our channel 1, and this is our R1P, and if we follow it, we can see that it is connected to ground. So we have our R2P not connected to ground, and this is the one that we will be measuring the output voltage versus the input voltage using the oscilloscope, which we have connected over here to Vin and over here to V out. So if we come over here, we can see a really nice figure in the oscilloscope, and this is basically what we've been measuring over here. Our channel 1 represents our Vn, and it says peak to peak around 2.2, and then channel 2 peak to peak, that is our V out, which is the blue. And in this case, just to check and to remember, we still have the frequency of about 1.0 hertz. And let's see, here we have the peak to V out to be around 360 millivolts, and for Vn around 2.2. And if we check our chart here, we can see that
that's the second point.
This is going to be our point over here. So we have around 2.2 and 0.35, and that's how we calculated the V out over Vn actual, and then we know the rest. Alright, so now we're off to discussions and conclusions. So as we saw from our results, we definitely have percent errors that go around 5%, which is really good, which means our circuit is working the way we wanted it to work. And we also saw from the results section that we have weights that go from 0.1 to 10 for both V1 and V2. This V1 should be here. And these are the actual values. And yeah, 0.091, so around 0.1 and 0.926. 0.0926 is around 0.1. And then here we got really close to the 10 mark that we wanted. And it's important to notice that we actually turned all the way the pot to the minimum and the maximum value, as Mauricio explained in the other one. So that means that if you are a DJ who came and was playing around with both channels, you knew for sure that this would be the range about which you could increment the input or I guess decrease it. And of course, the most important part, it sounds really cool and it works. So that is basically it for 2-channel audio mixer. Hope you liked it. Alright, so this is Eminem, and we're going to be talking about noise canceling headphones. And so basically our purpose is very straightforward, very explicit in our title. This is a video about do-it-yourself noise cancel headphones. All you're gonna need is an op amp and 4 equal resistors. And so Mauricio is going to talk a little bit more about the design in a few minutes, but I just wanted to make sure we have this theoretical concept already in our mind about what the differential amplifier does. And basically all you need is the op amp, 4 resistors of equal magnitude. It doesn't really matter what their value is. And we need to remember that V out for this particular circuit is going to be V2 minus V1. No amplification. We're not going to be inverting the entire signal. We're going to be inverting V1. So it's a very straightforward circuit, and as we're going to see, it's going to be super useful for our purpose. So how do actually noise cancelled headphones work? In real life, you know, you have your headphones. Yes, these are headphones. And they capture some of the actual noise coming from outside. Let's say a baby crying or a truck or whatever it is. And they're going to generate a wave, so actual sounds, that is going to be the exact inverse of the noise that is coming through. And then they're going to be up in the air, and the noise is going to be cancelled. So that's how they work.
So this is Team M&M again, and we are going to explain our design methods. So for this circuit, as Maria already explained, we're using a differential amplifier, and it looks like this. This is a regular op amp, and we have 4 resistors, which are all the same size, and the component values we used are all very close. The only one that's different is within 0.02%, which we consider negligible for this appliance. So the point of this circuit is that we are going to connect only noise always to V1, and we're going to connect noise plus the track to V2, or only noise just for testing. So that comes from the fact that in a differential amplifier, V out is equal to V2 minus V1. So this minus V1 will already invert our noise and add it up to the original track. So that way, if we use noise on both, we're supposed to get 0, and we'll test that. And if we use the noise plus the track in one and just noise in the other one, we're gonna get only the track out, and we're gonna hear a clean sound. So basically, the noise in this case, the noise comes from a track, but it can always come from a microphone that picks up a baby crying, or a truck, or a jet. There are many sources of noise, but it just is there to be added up to the noise plus the track. The inverse will be added up, and we get no output.
Alright, so this is M&M again, and we're about to try the noise cancelling headphones. So just to start, we're gonna be trying, you know, putting noise into V1 and grounding. So in this case, our V1 is here. So we have it connected, as you can see, to the computer. And we're gonna be seeing on the screen our channel 1 is gonna be this V1, which is going to be generated by the computer. And our channel 2, we have it grounded. So we're just going to be putting the noise input into V1. So we're going to see in the oscilloscope how the output will be inverted, because V1 inverts it. And then later on, we're going to see what happens with V2, which hopefully is not going to invert it. So let's hit play. Alright, so again we have noise, and it's pretty clear how it is inverting it. And right now, as we said before, we're in V1, so this blue is the output and this is the input signal V1, and we have V2 grounded. So now we're gonna try grounding V1 and putting the input signal in V2. So this is M&M again, and right now, as we said we were going to do, we are grounding channel 1, which is this one up here. We're grounding it, and we're taking the input signal from V2, which is coming from here and there. So that means that the yellow over here is going to be the input signal in V2, and the blue is going to be the output, as always. And we should again hear it because we're just putting noise in V2. So let's see what happens. Alright, so we want to see how V2 is not being inverted or amplified, as opposed, as we just saw with V1, how it was being inverted. So we're going to play it again, and we're going to stop the oscilloscope, and we're going to check out the image. So let's see it. So that's the noise, as we expected. And yay, we can see clearly how it is not being amplified and it's not being inverted, because that's what we designed it for. And this is the yellow again is the input V2 and the blue is the output. So now let's see what happens if we put V1 and V2 both with the same input, which is going to be the noise. So as we promised, now we're going to try putting the same input signal in V1 and V2. So the way that we did it, and we can see clearly here, is that we have this little cable connected to the computer, and this input is going to be connected to both the V1 and the V2. And in the oscilloscope, what we're going to see, as usual, V out is going to be in blue and V in is going to be in yellow, and our V in is going to be the same for V1 and V2 because it's the noise. So what we're hoping to see is that the blue line stays flat and the yellow line obviously has some signal. So let's see what happens. Oh, look at that. We don't hear anything at all, and we have yellow going around and blue staying still. And we didn't hear a thing.
So now we're gonna check how our noise canceling headphones actually cancel noise from a regular sound. So first, we grounded our V in where we're supposed to input the noise channel alone, and we only connected the noise with the voice from Toy Story. And here in the oscilloscope, we're not gonna see anything for our yellow one because yellow one is connected to V1, which is grounded, but we are supposed to see V out in the blue one, and that's the sound, and it looks like this. So now what we're gonna do is we're gonna connect into V1, we're gonna connect our channel that has only the noise. And in order to do that without any time delays, what we did is we used the computer and separated them into a right and left channel. So that way we're doing it all at the same time, and you can see that the noise is only in the left channel, and that's going into channel 1, the white wire in the board, and the noise plus our music is going into the into the right channel alone. So when we play it,
and just keep an eye out for hearing the difference, because before it was really clear there was the jet noise in the background. So now let's see what happens when we plug the noise and the noise plus the track.
I have been chosen. Farewell, my friend. I go on to a better place.
So when we looked at the oscilloscope, and we can do this again, you can notice how the yellow, which is the noise alone, is cancelled, and we get a really clear sound.
Farewell, my friend. I go on to a better place.
I think that's it.
So now we're gonna hear just the close-up of the actual audio of how our noise canceling headphones work. So let's see how it works.
I have been chosen. Farewell, my friend. I go on to a better place.
And now we're going to compare this to when we don't have the other noise input signal coming in, and we just have the track with the noise added. And this is like what we're trying for you to hear is the big difference between both audible tracks. Let's see.
I have been chosen. Farewell, my friend. I go on to a better place.
Awesome. Alright, so now we're going to talk about conclusion and discussions. So as we saw, our circuit works really well. There aren't many, or actually we couldn't find any at all, discrepancy between the theory and what we predicted was going to happen. So we're just basically going to do a little recap of what the experiment did. So we found R's that were all the same for a circuit. We just had one that was about 0.02%, which isn't really different from all of the other R's. And as we said before, the resistors in this difference amplifier, the only thing that matters is that they are all the same, so that we don't have weird gain. So it doesn't really matter which resistor you pick as long as they're all the same. We saw that it definitely works. Yay, it actually works really well. We didn't have any gain when we saw it in the oscilloscope, or when we saw in the video the VPBs were not different. We didn't have any amplification or decrease in the amplitude. It was pretty much the same. We also showed that V1 works independently from V2 in the part that we grounded one of these two, and then we put in the noise in the other one. So that part showed that they work independently. And then when we saw in the oscilloscope, V1 in fact inverts the signal and V2 doesn't. So that is definitely telling us that our equation for when we put V1 input and V2 input, in the end, our output is going to be V2 minus V1, which is exactly what we wanted. And in the case of the noise, in which we put V1 noise and V2 noise, we got 0. We got a flat straight line. And in the case when we had V1 with noise and V2 with track plus noise, we definitely got V out just a track, and it was pretty clean and nice. Something that we should definitely mention is the timing. So at the beginning we thought our circuit wasn't working, but that was just because I was pressing one button while Mauricio was pressing the other, so because we had two different inputs. And it is important for us to say that timing is really important. So what we did is that we used a program called Audacity, and basically what it does is that it's going to play the two things, so V1 and V2 is going to just trigger them at the exact same time, and that is what we wanted. So that is basically about it. If you have any questions, let us know. I hope you enjoyed our own do-it-yourself noise-canceling headphones. So this is Eminem, and now we're doing the video for the competitor. And even though we were not supposed to do a video for this one, we think it's going to be easier for us to see in the future, and just for us to show what the oscilloscope is showing at different stages of our circuit. So this is the circuit diagram, and in here we're showing some of the actual values, and there was a boo-boo, and the boo-boo was basically that we needed to add a resistor before the LED, so that you know, the current going through it was around 20 milliamps, and it wasn't too big so that it would like burn out. So Mauricio is going to explain real quick how changing the pot is going to change our output, and that's basically going to be changing this pot over here, which is this one we have here. Is going to change what is coming into V minus compared to what we have in V plus, which is our signal generating. Alright, so right now I'll pass you to Mauricio.
So we basically have a sine wave, and when the pot is to the minimum resistance, we're going to get 5 volts into V minus. So basically, our sine wave never goes above 5 volts. So if we don't go above, if we don't get to that value, it's always greater. And the LED does not turn on, and our blue line does nothing, our channel 2 measurement. But if we turn this up, at some point we start having comparisons. So you can notice that when the sine wave is positive. Getting there? Okay.
Oh, there it is.
When the sine wave is positive or above a certain value that we're comparing, the light turns on and we get a positive spike. When it's negative, we get a negative spike. And if we turn it all the way, we have the light turn on whenever it's positive and be off whenever it's negative. And that's basically what it does. It compares whether one is greater than the other, but we're comparing between the sine wave and zero.
Yeah, and again, what we're seeing here, obviously this is the output, in which we can see it's completely saturating when it's greater than the other, in this case, V plus, which is what we're comparing it to. And changing the pot is also going to change how the frequency at which the little light is blinking, just because of what